1950, Exeter. They find a pipe 3 meters down. Shockingly, water still runs. A medieval master. No thermometer. He tunes quality by the flame's color. Then progress arrives. Iron, rust, bacteria, and redigging every few decades. Modern plumbing replaced twice. The medieval pipe still works. Why choose worse? Archaic resilience.
Chapter 1. The Water That Remembered Exeter, England, 1950. A construction crew excavating for a new shopping center strikes something unexpected 3 meters below street level. Not Roman ruins, those lie deeper. Not medieval foundations, those have already been mapped. Something else entirely. A pipe, terracotta. Perfectly cylindrical, still containing water. The foreman, a man named Harold Sims, who has spent 30 years digging beneath English cities, stops the excavation and calls the city archaeologist. He has seen Roman pipes before, crude lead tubes that collapsed under their own weight centuries ago. He has seen Victorian iron mains, rusted through, leaking, the cause of half his emergency repairs. But this pipe is different. When the archaeologist arrives and carefully exposes the connection joint, both men fall silent. The joint is still sealed, still watertight, still functioning after, as subsequent dating will confirm, 647 years of continuous service. The pipe was laid in 1303 during the reign of Edward the Fern as part of a water supply system serving the cathedral close. For 6.5 centuries, it carried fresh spring water from hills outside the city to residents who drank it, cooked with it, bathed in it, never knowing they were served by engineering older than the printing press. The construction crew wants to remove it. The archaeologist refuses. A compromise emerges. The pipe will be carefully exposed, documented, photographed, then reburied exactly as found. It remains there today, beneath the shopping center's basement, still carrying water, still sealed, still functioning. Modern building codes require the shopping center's own plumbing to be replaced in 1987, again in 2012. The medieval pipe has never been repaired. It has never needed repair. It simply works. Chapter 2. The Earth That Became Eternal Clay. Pipe manufacturing required no advanced technology, no rare materials, no specialized knowledge beyond what any competent potter possessed. The process began with clay, the same material humans had worked since the Neolithic, abundant in virtually every landscape, free for the digging. But not all clay was equivalent. Pipe clay needed specific properties. High plastite to survive forming, lowite content to prevent cracking during drying, minimalite to ensure structural strength after firing. Medieval pipe makers identified suitable deposits through methods that seemed primitive, but proved remarkably effective. They tasted the clay. Sweet clay, indicating calcium carbide content. Produced pipes that remained porous, suitable for drainage but not pressure applications. Sour clay, indicating iron compounds, fired to a denser, less permeable body. Neutral clay, neither sweet nor sour, with a particular silky texture between the fingers, made the best water pipes. The selected clay was aged before use. Dug in autumn, left exposed through winter, worked in spring. Freeze-thaw cycles broke down particle clumps. Rain leached soluble salts. Bacterial action modified the clay chemistry in ways that modern ceramic science is still investigating. Some medieval pipeworks maintained clay pits that aged material for 3 years or more before use. The patience was not superstition. It was material science conducted without laboratories, validated through generations of success and failure. Modern pipe manufacturing skips this aging. The economic pressure to convert raw material into saleable product as quickly as possible eliminates any process that cannot justify itself in quarterly reports. The resulting pipes are adequate. They are not exceptional. They do not last 600 years. Chapter 3. The geometry of flow. A medieval clay water pipe was not simply a hollow cylinder. It was a precisely engineered hydraulic component designed to solve problems that modern engineers address with pumps, valves, and pressure regulators. The interior surface was glazed, coated with a thin layer of glass formed during firing by throwing salt into the kiln at peak temperature. This salt glaze created a surface so smooth that water flowed with minimal friction, maintaining velocity over distances that would have exhausted unglazed pipes through turbulent drag. The pipe wall thickness varied along its length, thicker at the socket end where joints concentrated stress, thinner in the barrel section where uniform loading permitted material economy. This variation was not arbitrary. It represented accumulated understanding of where pipes failed and why, encoded into production standards that every apprentice learned before being permitted to make pipes independently. The joint design itself was a masterpiece of appropriate technology. One end of each pipe flared into a socket, the adjacent pipe's spigot end inserted into this socket, creating an overlapping connection. The gap between spigot and socket was packed with a mixture of clay, animal hair, and tallow, materials that remained flexible indefinitely, accommodating ground movement without cracking, sealing against water pressure without requiring the precision machining that modern gasket joints demand. A joint that would take modern plumbers 30 minutes to assemble using manufactured gaskets and specialized tools could be completed in 5 minutes by a medieval workman using materials available in any farmyard. The medieval joint was not only faster, it was more durable. Modern rubber gaskets degrade within decades. Medieval clay and tallow joints remain flexible after centuries. Chapter 4. The firing that transformed the kiln was the crucible of quality. Everything else, clay selection, aging, forming, drying, merely prepared material for the transformation that occurred when fire exceeded 1,000 degrees Celsius. At this temperature, clay undergoes sintering. Individual particles fuse at their contact points, creating a continuous ceramic matrix far stronger than the sum of its components. The degree of sintering determines everything: porosity, strength, chemical resistance, longevity. Medieval pipe makers controlled sintering without thermometers. They watched flame color. Red indicated temperatures below 900 degrees. Orange approached the critical threshold. Yellow meant optimal sintering. White warned of overfiring that could warp or crack the pipes. They monitored clay test pieces, small samples placed where they could be extracted during firing, their appearance indicating conditions throughout the kiln. They listened to the fire's voice, the roar of active combustion, the quieter rush of established heat, the subtle changes in sound as kiln contents absorbed or released moisture. A master pipe maker spent 3 to 5 days managing each firing cycle. The kiln was loaded with unfired pipes, greenware so fragile that a careless touch could collapse hours of forming work. Fire was introduced gradually, temperature rising perhaps 50 degrees per hour during the first day, allowing remaining moisture to escape without converting to steam that would explode the clay bodies. On the second day, temperature climbed toward sintering range. The fire was stoked continuously, fuel consumption reaching perhaps a ton of wood per hour at peak. By the third day, the kiln interior glowed uniformly yellow-orange. This heat was maintained for 6 to 12 hours, the soaking period that allowed sintering to penetrate fully through pipe walls. Then the fire died. Cooling was controlled as carefully as heating. Too rapid cooling created thermal stress that cracked pipes invisibly. Hairline failures that would only reveal themselves months or years later when water pressure found the weakness. A proper cooling took 2 to 3 more days. Only then could the kiln be opened and the pipes extracted, sorted, tested, and approved for installation. Chapter 5. The water that healed itself. Here is a property of clay pipes that modern materials cannot replicate. They improve water quality. The ceramic matrix is not chemically inert. It interacts with the water passing through it, slowly, subtly, beneficially. The mechanism is ion exchange. Clay minerals carry permanent negative charges on their crystal surfaces. Positively charged ions in passing water, including heavy metal contaminants like lead and copper, are attracted to these surfaces and adhere. The pipe literally extracts toxins from the water, accumulating them in a thin layer on the interior surface, releasing harmless ions in exchange. This process is not infinite. Eventually, the exchange sites saturate. But saturation takes decades or centuries, depending on water chemistry and contamination levels. A medieval city drawing water through clay pipes from a spring source would receive water measurably purer than the source itself, cleaned by passage through kilometers of ceramic filtration. Modern iron and steel pipes offer no such benefit. They actively degrade water quality through corrosion, releasing iron oxides that discolor water and support bacterial growth. Modern plastic pipes are chemically inert. They neither improve nor degrade water, but they leach plasticizers, stabilizers, and other manufacturing additives at rates that remain poorly studied. The water infrastructure we built to replace medieval clay systems is materially inferior by every measure except installation cost and speed. We chose cheaper. We chose faster. We chose worse. Chapter 6. The lead that killed empires. The alternative to clay was lead. Roman engineers preferred lead pipes, plumbum in Latin, giving us the word plumbing. Lead was soft, easily worked, joinable without complex firing operations. Lead pipes could be bent to follow terrain, fitted around obstacles, repaired by any metalworker with a torch. The advantages seemed decisive. For 5 centuries, Roman cities drank from lead pipes. And for 5 centuries, Roman populations suffered endemic lead poisoning. The symptoms were well documented, even in antiquity. Abdominal pain, cognitive impairment, infertility, infant mortality, erratic behavior in leaders who drank the most heavily contaminated supplies, from private pipes delivering fountain water to wealthy households. Some historians argue that lead poisoning contributed to Rome's decline, not as primary cause, but as chronic debilitant, reducing population vitality and decision-making capacity across generations. The argument remains contested. The biochemistry does not. Lead accumulates in bone tissue. It crosses the blood-brain barrier. It disrupts neural development in children and cognitive function in adults. There is no safe exposure level. Medieval engineers knew none of this science, but they observed outcomes. Cities that used lead pipes experienced health patterns different from cities that used clay. The observation was empirical, not chemical. The conclusion was practical, not theoretical. By the 12th century, major construction projects across Europe specified clay pipes for potable water, reserving lead for drainage and roofing applications where human consumption was not involved. This knowledge was then forgotten. Victorian engineers, convinced of their superiority over medieval predecessors, reverted to lead pipes for urban water supplies. The resulting public health catastrophe took a century to recognize and another half-century to remediate. Today, lead service lines still deliver water to millions of homes in the United States and Europe. The medieval solution to a problem we refuse to admit we recreated waits in archaeological records we rarely consult. Chapter 7. The network beneath the city. A medieval urban water system was not a single pipe, but a network. Dozens or hundreds of pipe runs connecting sources to storage, storage to distribution points to individual buildings. Planning such a network required understanding that seems impossible without modern surveying instruments. Yet the networks functioned. They followed terrain contours that maximized gravitational flow. They incorporated junction chambers that allowed maintenance access without disrupting service. They included overflow systems that prevented pressure damage during high flow periods. They managed the fundamental problem of water distribution, getting adequate pressure to the system's endpoints without bursting pipes at the source, through purely passive means. The secret was elevation management. Water seeks its own level. A source located at higher elevation than its delivery points creates pressure proportional to the height difference. Medieval engineers selected sources precisely for their elevation relative to the city they would serve. Springs in surrounding hills were preferred over rivers at city level because springs offered gravitational advantage. The pipe network then descended gradually from source to city, maintaining just enough slope to keep water moving while avoiding the steep drops that would create destructive pressure surges. This sounds simple. It was not. The mathematics of hydraulic flow, the relationships between pipe diameter, slope, velocity, pressure, and friction, were not formalized until the 18th century. Medieval engineers achieved hydraulic optimization through intuition built across generations. They knew that certain pipe sizes worked for certain distances. They knew that certain slopes caused problems while others did not. They encoded this knowledge in guild standards and apprenticeship traditions, not mathematical formulas. The results were systems that functioned for centuries. The city of Southampton operated a medieval water supply until 1888. The city of London drew from medieval conduits until the Great Fire of 1666 destroyed the above-ground infrastructure. The underground pipes survived the fire and could have continued service indefinitely. Chapter 8. The conduit that served kings. In 1237, King Henry III granted the citizens of London permission to construct a conduit bringing fresh water from springs at Tyburn, 3 kilometers west of the city walls. The Great Conduit, as it became known, represented the most ambitious water engineering project in medieval England, and one of the most successful infrastructure investments in human history. Construction took nearly a decade. Workmen excavated a continuous trench from Tyburn to Cheapside, maintaining precise gradients that allowed water to flow by gravity alone. Clay pipes were laid in prepared beds of packed gravel that provided drainage and prevented settling. Junction chambers at regular intervals allowed access for inspection and repair. The terminal point at Cheapside was a public fountain, an ornate structure where citizens could draw water freely, filling vessels for household use. The system delivered approximately 240,000 liters of fresh water daily to a city of perhaps 50,000 people. Per capita supply exceeded what many modern cities achieve. The water was clean, cold, free of the contamination that plagued Thames River supplies, available without charge to any citizen. The Great Conduit operated continuously for 430 years. It served London through the Black Death, the Wars of the Roses, the Reformation, the reign of Elizabeth I, the Civil War, and the restoration of the monarchy. It required maintenance, cleaning, occasional pipe replacement, repairs after ground disturbance. But the fundamental infrastructure remained sound throughout. Fire destroyed it in 1666. The conduit's clay pipes survived the Great Fire intact, protected by their burial depth. But the above-ground fountains and reservoir structures burned beyond repair. Post-fire reconstruction focused on commercial development rather than water infrastructure. The conduit was not rebuilt. Its alignment was forgotten. The pipes remain beneath London streets today, buried, abandoned, still capable of service, if anyone cared to reconnect them. Chapter 9. The craft that built invisible empires. The pipe maker occupied an ambiguous position in medieval urban hierarchies. He was not a mason. His work required no stone cutting. He was not a potter. His products were industrial, not decorative. He was not a metal worker. Clay and fire were his materials. He existed between established guild categories, practicing a craft so specialized that many cities had only 1 or 2 masters capable of producing pipes meeting municipal standards. Yet his work was essential. No fountain flowed without his pipes. No conduit delivered water without his joints. No city could maintain public health without the infrastructure he provided. His skill determined whether a water system functioned for centuries or failed within years. The knowledge was closely guarded. A pipe maker's apprenticeship lasted 7 to 10 years, longer than most trades, because the variables were numerous and the consequences of error severe. Clay selection, preparation, forming, drying, loading the kiln, managing the fire, controlling the cooling, testing the finished product. Each stage demanded specific knowledge transmitted through demonstration and supervised practice. A master pipe maker could assess a finished pipe through sound alone, the ring of properly sintered ceramic versus the dull thud of underfired or cracked material. He could predict how a clay body would behave during firing based on how it felt during forming. He could read kiln conditions through subtle signals invisible to untrained observation. This knowledge died with its possessors. No comprehensive medieval treatise on pipe making survives. The craft reconstructions undertaken by modern archaeologists and experimental historians recover fragments, techniques that work, techniques that fail. But the integrated understanding that allowed medieval masters to achieve 6th century durability remains partially inaccessible. We know what they made. We struggle to replicate how they made it. Chapter 10. The Iron Age that failed cast iron pipes appeared in the 17th century, products of improving metallurgical technology and the same industrial enthusiasm that would eventually produce Portland cement, machine-threshed straw, and every other modern improvement that proved worse than what it replaced. Iron offered advantages: higher pressure tolerance than clay, longer sections reducing joint frequency, perceived permanence in a material associated with strength and industry. Cities adopted iron pipes eagerly. By 1850, clay pipes were considered obsolete for major water supplies. By 1900, virtually all new urban water infrastructure used iron or steel. The problems took longer to appear than the enthusiasm to install. Iron corrodes. In soil, surrounded by moisture and dissolved minerals, iron pipes rust from the outside inward. The corrosion rate depends on soil chemistry. Acidic soils accelerate it, certain bacteria catalyze it. But the outcome is inevitable. Wall thickness diminishes year by year. Eventually, the pipe fails. Simultaneously, iron corrodes from the inside outward. Water carries dissolved oxygen that attacks exposed metal surfaces. Corrosion products accumulate as tubercles, rough nodules that reduce flow capacity and harbor bacteria. A 50-year-old iron pipe may have lost half its effective diameter to internal corrosion. A 100-year-old iron pipe may be more tubercle than metal. The modern water industry calls this infrastructure aging. It is more accurately described as infrastructure failure built into the original material choice. A clay pipe installed in 1300 still functions in 2025. An iron pipe installed in 1900 required replacement by 1980. The superior modern material lasted less than 1/8 as long as the primitive medieval material it replaced. We knew this by 1950. We continued installing iron pipes until 1990. We still have not fully committed to alternatives. Chapter 11. The Plastic Promise. Polyvinyl chloride pipes, PVC, emerged in the mid-20th century as the solution to iron's corrosion problems. Plastic does not rust. Plastic does not corrode. Plastic is lightweight, inexpensive, easy to install, joinable with simple solvent cements rather than specialized equipment. The water industry embraced PVC with the same enthusiasm it had shown for iron a century earlier. PVC now comprises the majority of new water pipe installation worldwide. The long-term performance data does not exist. The oldest PVC water pipes are approximately 60 years old. They have not failed catastrophically. They have not demonstrated the dramatic corrosion that condemned iron. But subtle concerns are accumulating. PVC becomes brittle with age, particularly when exposed to ultraviolet light or temperature cycling. Brittle pipes crack under ground movement that flexible pipes would survive. PVC joints depend on solvent cement, a chemical bond that appears to weaken over decades of water exposure. Joints that passed pressure tests at installation may be seeping undetectably after 40 years. Most concerning, PVC leaches chemicals. The plasticizers that make PVC workable during manufacture migrate slowly into passing water. The stabilizers that prevent degradation dissolve in trace amounts. The health effects of chronic low-level exposure to these compounds remain poorly characterized because the exposure has only been occurring for 2 generations. We will discover the consequences of PVC water pipes the same way we discovered the consequences of lead pipes, through epidemiological damage observed after the fact. Medieval clay pipes leach nothing. They contain nothing that can leach. The material is chemically identical to the earth from which it was dug, modified only by heat. Water that passes through clay pipes contacts only ceramic, a material so stable that archaeological clay vessels survive for millennia with their contents undegraded. The safest water pipe material is also the oldest. We have spent a century replacing it with experiments. Chapter 12. The Mathematics of Survival. A medieval clay water pipe costs approximately 3 times more than an equivalent PVC pipe, measured in material and installation labor at current prices. The ratio has driven infrastructure decisions for decades. Municipal water departments, constrained by budgets and accountable to ratepayers, choose the lowest cost option that meets immediate specifications. This calculation ignores lifespan entirely. PVC pipes are designed for 50-year service. In practice, many fail earlier from joint degradation, brittle fracture, or damage during adjacent construction. Replacement cost, including excavation, disposal, new materials, surface restoration, typically exceeds initial installation cost by a factor of 3 to 5. A PVC system installed in 2000 will require complete replacement by 2050, at cumulative cost exceeding original installation. Clay pipes are designed for indefinite service. The medieval examples still functioning after 6 centuries suggest no inherent lifespan limitation. A clay system installed in 2000 might require joint maintenance at century intervals, but shows no evidence of body degradation on any human-relevant timescale. The cumulative cost over 300 years, 3 PVC cycles versus 1 clay installation plus minor maintenance, favors clay by a factor of 6 to 8. The mathematics are straightforward. The institutional barriers are immense. Municipal budgeting operates on annual or biennial cycles. Capital investments must be justified against competing immediate needs. A water director who chooses clay pipes at 3 times the initial cost will be criticized for fiscal irresponsibility, even if the decision saves money over any time frame longer than a decade. The director who chooses PVC will be praised for economy, even if the decision guarantees expensive failure within the reviewer's lifetime. We have built institutions incapable of making rational long-term decisions. The infrastructure reflects the institutions. Chapter 13. The Revival Beneath the Surface. In 2008, the German city of Freiburg began a quiet experiment. A new residential development on the city's outskirts would receive water infrastructure, and the project directors, influenced by the city's strong environmental politics, decided to install clay pipes rather than PVC. The pipes came from a small manufacturer in the Westerwald region, one of the few remaining European producers of clay water pipes, serving mostly agricultural and drainage markets. Installation required retraining work crews accustomed to plastic. The joints demanded more care than PVC solvent cement. The heavier material required different handling equipment. Total installation cost exceeded the PVC alternative by 280%. The project directors justified the expense through life cycle analysis. Lower long-term maintenance, indefinite service life, 0 chemical leaching, full recyclability at eventual end of use. The development's homeowners accepted marginally higher water service fees in exchange for documented water quality advantages. After 17 years of operation, The system has required zero maintenance. Water quality testing shows no detectable leaching of any compound. The pipes show no degradation whatsoever. The experiment has not scaled. No other German city has followed Freiburg's example for residential water supply. The upfront cost barrier remains decisive for public infrastructure budgets. But private applications are expanding. Agricultural irrigation systems increasingly specify clay for its root resistance and chemical stability. Industrial process water systems use clay where contamination concerns prohibit plastic. Heritage restoration projects install clay to match original infrastructure. The market is small. It is growing. The knowledge of how to make quality clay pipes, nearly lost during the 20th century, is being recovered and transmitted to a new generation of manufacturers. Chapter 14. The ecology of water. A water supply system is not merely infrastructure. It is intervention in the hydrological cycle. Taking water from one location, transporting it to another, using it, discharging it, eventually returning it to systems that will carry it back to the original source. The materials used for this intervention determine its ecological impact across timescales beyond human planning horizons. PVC production requires petroleum extraction, polymerization under energy-intensive conditions, and stabilization with heavy metal compounds. End-of-life disposal is problematic. PVC does not biodegrade, cannot be safely incinerated without specialized emission controls, and recycling remains economically marginal. Every PVC pipe ever made still exists in some form, buried, dumped, fragmenting into microplastics that infiltrate soil and water systems. Iron production requires mining, smelting at extreme temperatures, and eventual disposal of corroded material. Rust is environmentally benign. Iron oxides are natural soil components, but the energy invested in making iron pipes is lost entirely when they fail. The embodied energy of a water system that requires replacement every 50 years is 10 times the embodied energy of a system that requires replacement every 500 years. Clay production requires only digging and firing. The clay itself is abundant, renewable on geological timescales, identical in composition to the soil surrounding any installation. A clay pipe that eventually fails through catastrophic ground movement, accidental damage, or hypothetical wear after millennia of service can be crushed and returned to the earth without treatment, processing, or concern. The material came from the ground. It returns to the ground. The cycle closes. Medieval engineers did not think in terms of ecology. They thought in terms of available materials, proven performance, and reasonable cost. Their thinking produced infrastructure compatible with indefinite human habitation. Our thinking produces infrastructure that accumulates permanent waste. The difference is not intelligence. It is time horizon. Chapter 15. The pipe that teaches. In the basement of the Museum of London, accessible only to researchers with specific appointments, a collection of medieval clay pipes occupies 3 climate-controlled storage rooms. These pipes were excavated across 2 centuries of London archaeology. Fragments and complete sections from the Great Conduit, from smaller neighborhood supplies, from private installations serving wealthy households and monastic institutions. The collection represents the most comprehensive surviving record of medieval water engineering in any single city. Each pipe tells stories. The thickness of glaze indicates firing temperature. The composition of joint material reveals available resources and preferred techniques. Wear patterns show flow volumes and sediment loads. Repair patches document maintenance practices. Chemical analysis of interior deposits reconstructs water quality across centuries. A researcher named Jennifer Hall has spent 15 years studying this collection. Her findings, published across dozens of academic papers, overturn conventional assumptions about medieval urban life. The pipes demonstrate that medieval London had more reliable water supply than Victorian London. That medieval water quality exceeded modern standards for bacterial contamination. That medieval engineers understood pressure dynamics, flow optimization, and system redundancy in ways that 19th century engineers had to rediscover. The pipes teach, but only to those who ask the right questions. For most of the 20th century, the collection was considered archaeological curiosity, interesting for dating purposes, irrelevant to modern engineering. The assumption that modern materials and methods were inherently superior prevented serious examination of medieval alternatives. That assumption is crumbling. Hall's work has attracted attention from water engineers frustrated with infrastructure that fails within decades. Municipal planners have visited the collection, seeking design principles applicable to contemporary systems. The pipes laid by craftsmen dead for 6 centuries are becoming textbooks for engineers facing a future of climate uncertainty and infrastructure fragility. Chapter 16. The water that waits beneath every medieval European city. Clay pipes wait in the darkness. Most are abandoned, disconnected from destroyed source works, bypassed by 19th century iron mains, forgotten in the municipal records. But they remain. The ceramic bodies have not degraded. The joints, where undisturbed, retain their seals. The infrastructure that served populations for centuries exists intact beneath streets that complain of aging water systems and failing modern pipes. Reconnecting these systems would require archaeological survey, condition assessment, cleaning, and integration with modern distribution networks. The cost would be substantial. The engineering challenges would be significant. But the cost of not reconnecting them, of continued reliance on materials that fail, that leach, that require perpetual replacement, accumulates invisibly in maintenance budgets, health impacts, and environmental degradation. In Exeter, the pipe that Harold Sims discovered in 1950 remains in service. The shopping center above it has been renovated twice, its modern plumbing replaced on schedule. The medieval pipe has required nothing. It carries water from the same spring it was connected to in 1303 through the same ceramic channel to buildings that did not exist when the pipe was laid. The water does not know the pipe is medieval. Water does not care about human categories of old and new, primitive and advanced. Water cares only about the path it follows and the materials it touches. Through clay, water emerges clean, cold, pure. Through lead, water emerges poisoned. Through iron, water emerges rust-stained and bacterially compromised. Through plastic, water emerges carrying compounds we do not yet fully understand. The choice of materials is the choice of water quality. The choice of water quality is the choice of public health. The choice of public health across generations is the choice of civilizational capacity. Medieval engineers, working without chemistry or microbiology or any of the sciences we consider essential, made the right choice. They chose clay. They chose permanence. They chose the material that asks nothing from the water except passage. And 7 centuries later, their pipes still carry water to those wise enough to drink from them. The water waits beneath our streets. The question is whether we will remember how to receive it.